Welcome to this comprehensive guide on creating player movement in Unity 3D using a custom C# function, perfect for beginners. We will walk through each step, ensuring you understand the core concepts and implementation details for effective player control. We'll start by setting up a simple scene in Unity. This involves creating a new project, specifically selecting the 3D core template and preparing our environment for player interaction. This foundational step is crucial for any game development. Next, we'll create a player object. For simplicity, we'll use a basic primitive like a capsule. It's important to rename it to player for easy identification and organization within your project hierarchy. To give our player a surface to move on, we'll add a ground plane to the scene. This ensures the player has a stable environment and is positioned correctly, preventing it from falling endlessly. For physics-based movement, we need to add a rigid body component to our player. This component allows the player object to interact with Unity's physics engine, enabling realistic movement and collision responses. Now, let's create a new C# script named Player Movement in our project window. This script will be the central place where we house all our custom movement logic and control the player's actions. Double-clicking the script will open it in Visual Studio, your integrated development environment. Here, we'll begin the exciting process of writing our movement code, bringing our player to life. We'll declare a serialized float variable for speed. By using serialize field, we make it adjustable directly within the Unity Editor's inspector, allowing for easy tweaking without modifying the code itself. We also need a rigid body variable to reference our player's physics component. Additionally, we'll declare float variables for horizontal and vertical input, which will capture player commands from the keyboard. In the start method, which is called once when the script is enabled, we'll get a reference to the rigid body component attached to our player object. This ensures our script can communicate with the physics engine. Within the update function, which runs every frame, we'll capture input from the horizontal and vertical axes using input.getAxisRaw. This method provides raw input values, typically -1, 0, or 1, for precise control. Next, we create a vector3 to represent our movement direction. This vector combines the horizontal and vertical inputs, translating them into a three-dimensional direction for our player to move in. It's crucial to normalize this movement vector. Normalization ensures consistent speed regardless of the direction, preventing faster diagonal movement and maintaining a smooth, predictable player experience. For physics-based movement, we apply this vector in fixed update, which runs at a fixed time step. We use rb.movePosition multiplied by our defined speed and time.fixedDeltaTime for frame rate independent movement. Alternatively, for non-physics movement, you could use transform, translate directly in the update function. This method moves the object's transform directly, bypassing the physics engine for simpler, direct control. Now, save your script in Visual Studio to apply the changes. Once saved, return to the Unity editor, where Unity will automatically compile your new code, making it ready for use. Select your player object in the hierarchy and drag the player movement script onto it in the inspector. This action attaches the script as a component to your player, enabling its movement logic. Then, drag the player object itself from the hierarchy into the RB field of the player movement script component in the inspector. This assigns the rigid body reference, linking our script to the player's physics component. You can also adjust the speed variable directly in the inspector. This allows you to fine-tune how fast your player moves without needing to go back into the code, offering great flexibility during development. It's time to test our movement. Press the play button in the Unity editor to enter play mode. This will run your game, allowing you to interact with your player and observe its behavior in real time. Use the W, A, S, D keys or arrow keys to move your player. Observe its movement on the ground plane, checking for smooth and responsive control. This is where you see your code come to life. If the movement feels too slow or fast, you can adjust the speed variable in the inspector even while in play mode. This live adjustment feature is incredibly useful for quickly finding the perfect movement speed. For more advanced input, consider Unity's new input system. It offers greater flexibility and control over input actions, allowing for more complex and customizable player controls beyond simple axis inputs. To prevent excessive speed, you can clamp the rigid body's velocity. This ensures your player doesn't move too quickly, especially after collisions or external forces, maintaining a controlled gameplay experience. For smoother acceleration and deceleration, explore functions like Vector3.SmoothDamp or Math.SmoothDamp. These functions provide a gradual change over time, making player movement feel more natural and less abrupt. Implementing a camera that follows your player enhances the gameplay experience. A well-configured follow camera keeps the action in view, providing a clear perspective of the player's movement and surroundings. Finally, integrating animations can make your player movement much more visually appealing and dynamic. Simple walk or run animations can significantly improve the player's visual feedback and overall game polish. You've successfully created basic player movement in Unity 3D using a custom C# function. This foundational knowledge is key to building interactive games. Keep experimenting and building your game development skills.